Hello everyone, I'm Shibiao from Huawei Cloud. Today I'm the first to give a topic about CVRP. First, I want to apologize for using video like that. The network here is unsteady, so I hope this form can enjoy you a smooth experience. Now let's start. My slides can be divided into three parts: the background, the algorithm we use, and finally the experiment result. Because I'm the first person to give a topic about CVRP, so I think it's necessary to tell you something about the background. The capacitated vehicle routing problem is a generalization of traveling salesman problem. You know, TSP is a very popular problem in operation research. And in CVRP, the single route can be split into disjoint ones, and each route has an upper limit of capacity sum. Let's look at the left picture. You will find many blue points on the plane, and the red number means the capacity of each customer. And you should find some routes to ensure that each customer is visited only once, and the total distance for these routes are as small as possible. And the right shows a possible solution, and the solution seems very good because you will find 4 disparate routes and the total distance is relatively small. And now let's move on. Then I will tell you something about the CVRP benchmark. There are many datasets for CVRP, and all valuable benchmarks are collected in CVRP lib. The website is on the bottom. And I want to point out that with the development of algorithms and computing power, the scale of CVRP datasets tends to be larger and larger. From the very beginning, maybe about n is equal to 50 or 100, and then n is equal to 1000, and finally it's about 10,000. Now let's move on the related work. In my opinion, the algorithm of CVRP can be divided into 2 categories: heuristic algorithms and exact algorithms. And the former are dominant to the latter, so we only focus on the former algorithms. You know, state-of-the-art heuristic algorithms often employ the population-based structure and design some effective recreate methods and maybe do some local search operators to explore the neighborhood better. Here, I list some of the representative algorithms in recent years. First is from Nagata 29, the Age Assembly Crossover, EAX. And then the Hybrid Genetic Search from Vito 2012. And Vito has updated his method in 2022 with a brand new swap star technique. And then the KGLS, the SISR, the pop music, and finally the fast iOS localized optimization from Acosi in 2020. I will pronounce it as Philo. We focus on 2 types of heuristic algorithms, the population-based and the iterative local search. The former usually get a good performance at the cost of slow convergence on large-scale datasets. Conversely, the iterative local search algorithms usually run very faster because it only optimizes a single solution, but it is not stable. So, our fast hybrid CVRP solver wants to combine the advantages of above algorithms to minimize the time-distance integrals scored by the DIMACS offshore tracker. We will divide the instance roughly into the three parts: small, medium, and large. For small scale of instance, we directly apply Vidal's HGS to reach the almost optimal solution within a short time. For medium data, Acous's Philo is first used to obtain a relatively good solutions within a short time because the iterative local search is very fast. And then in the remaining long time, HGS is applied to optimize the solutions. And for large scale of instance, we apply a iterative Philo approach with increasing number of runs to optimize the solution gradually. These three methods used in our solver are named by HGS, Philo HGS, and iPhilo. So now we will prove that our division is very efficient. We do a study inspired by Vidal. We run 4 dependent algorithms: Philo, HGS, Philo long, and FHCSolver. The former 3 algorithms are directly from their authors, and the final algorithms is our solver. And we monitor each algorithm's progress up to a time limit of t equals 2.4 multiply n seconds. During each run, we record the time gaps curve to measure the performance of the algorithms at different stages of the search. You can imagine the result. From the perspective of descent speed, Philo must have a very good speed, and we imagine that our FHCSolver is similar with Philo. And as the final gap for small or big data, we also imagine that FHCSolver get a very good performance for the small data. It should be similar with HGS. And for the big data, HGS is population-based is not suitable, and we think the FHCSolver needs to smaller or similar with the Philo long. Here is the 4 pictures about the result of our experiment. For the top left picture, I will point it. This picture is the result among the all data, and our FHCSolver. You will see that this green curve is totally on the bottom. It means that our method is successful. So why get this result? Let's divide the data into small, medium, and large. Small, medium, and large. For the small data, we directly use HGS approach so that you can see the red and green curves are overlap. And the Philo maybe is not suitable for small data. And for the medium data, this picture, you will find that finally the green curve is overlap with the red curve because we finally use HGS, and the result is similar. But at first, our solver will have a very fast convergence speed, just like the FIAO. And for the large data, you'll find that the red curve, the HGS, is not suitable. So we first similar with philo, and these curves are overlap. And then the philo is not suitable, and we do a iterative philo. So our result is similar with philo long. But because we are the iterative approach, so finally we can still go down. So these three pictures finally integrate this. Okay, let's move on. Now, let me tell you about our modification to philo. Our goal is to find a relative good solution as fast as possible. So our demand to speed is very high. We adopt a closest SMD structure to explore each local search operator thoroughly with fast gradient descent. But we give up the two-stage HRVND because the ejection chain in the second stage is quite slow. And we also use blink mechanism. The blink mechanism was used in SISR, and we found this strategy also has a good result in our experiment. According to our experiment, the score of adding blink mechanism is about 20% better than that of not adding. But we also found that the blink rate value is not very important. That's to say, if we set the value to 0.05 or 0.2, we will have the similar result. And inspired by COSI, we use a simpler but also efficient structure to maintain local search in philo. The core structure is here. First, we focus on this list L. It is the metadata of all the possible pairs we are interested. The first two numbers is the pair, and this number is the distance delta if we apply this pair. And this number records the position in a heap, SMD structure also maintain a heap to quickly check the pair with the smallest delta value. And there are also some linked lists to quickly find the index of some pair, like neighbors 1. It means that it records all the pairs that associated with customer 1, like this means 1, 3, and this means 1, 2. And it records the position just point to the list L. And finally, there is a hash table. The key of the hash table is all the pair, and the value is all the positions they appear. So, how do we use this hash table and other data structure? For example, if we want to shrink the neighborhood of customer 1, like if we want to remove the pair 1, 2, we will first find the value in the hash table. We will find all the positions appear, like the metadata, like the position in the heap, and like the corresponding other appearance for 1, 2. So we can just delete this pair, and we just pop it in the heap. And you will find that whether we add a pair or delete a pair, all the structures can be modified within O1 time, so it is very efficient. Okay, let's go on. And the above slide remains a question: how we categorize the data. The simplest way is to checking the value of customer number n, and we can just divide them into small, medium, or big. But we use a more complex method. We test all the results in the X benchmark, just 100 instance. And we fit a following function to divide the data into 3 parts. You will find the detail function in the green block. And we directly use this function to other datasets. And the code of the FHCSolver can be roughly divided to 3 parts: the HGS, the philo, including the iPhilo, and finally the integrated strategy. For the HGS part, we directly use Visual's open source code. You will find the website in the bottom. And the later 2 parts are implemented by ourselves. And there is a notice. The distance type between customers in official datasets are various. Some are rounded to integer, and others are remain to double. So, in order to accelerate the code, we use template to recognize these 2 situations separately. And all the parameters used in our solver are all reasonable without carefully tuning. First, for the philo part, we almost remain all the parameters with some necessary changes. I remember that the delta is decreasing from 0.5 to 0.3. And for the HGS part, we use all the parameters exactly the same with Windows because we just use his open source code. And for some strategy we added, we use very reasonable number. Okay, let's move on. We have won the first place over 16 teams in the first round by luck, and we are looking forward to the final results. Honestly, I'm very nervous. Okay, this is all my slides I want to share. So, is there any questions? And comments are also welcome. Thank you.